Okay, cappuccino. It is now Friday afternoon. I said I would post the solutions to today's warm-up at 2 o'clock. I already had a whole bunch of people come in with the answers, so shout out to Izzy, Kylie, both Sarahs, and Amber. Good job working out that warm-up and getting me your answers before I posted them. So we took this data, these scores, and we found the mean score. So when we did that, we got 75.3 from our graphing calculator, and the standard deviation, we got 8.35. And then we had to find what percentage of the students scored between this and that. So this would be the mean minus the standard deviation, which would give us 66.95. And this one, the mean plus the standard deviation, would give us 83.65. And we looked at the scores. If you look at the scores for that, that would be, let's see, greater than 66.95 would start right here, and less than 83.65 would be right here. If we count up how many that is, 1, 2, 3, 4, 5, 6, 7, 8. Anyway, I counted them. It's 19. 19 out of the total 26. Change that to a percent. It ends up being 73%. Was it 73.1? I think it was 73.1. No, I don't remember. Anyway, whatever it was, around 73%. Okay, so why were we doing this? Okay, so notice that most of the scores fell in the 70s. We had a lot in the 70s. So let me show you what I did with this. I actually made a dot plot with this because I wanted you to see the shape of the distribution. So here's my dot plot. So if we kind of come here and just get the shape of that, you'll notice it is a bell-shaped curve. It's a bell-shaped curve. And notice what else I put on here. I put, where is the mean? Here's the mean. That's 75.3 approximately. It's right around here. And then I also added the standard deviation and subtracted the standard deviation. So that's the mean minus the standard deviation. 66.95 is right here, so that's one standard deviation to the left. And then I put one standard deviation to the right. And then I did it again. I added another standard deviation that gets me over here. And I also subtracted a standard deviation, and I went over here. And notice what happens. The farther you get away from the mean, the fewer dots I have. So we can say that because we got this bell-shaped curve, we can say this is kind of normally distributed data. So normally distributed data basically means that everybody's about the same, where everybody's kind of crowded around the middle. And there are certain situations where you expect to get this bell-shaped curve. And where did I put my pictures of that? Here they are. So for example, if we were talking about IQ, so here's an example of IQ. So a little hard to see. Let's see if I zoom in. It also printed kind of fuzzy. I got this off the internet. So population distribution of IQ scores. So most people are of average intelligence, and then there's a few people who are really high IQs, and then there's a few people who have very low IQs, but most people have average intelligence. So when we're measuring something where we expect people to all be about the same, we would expect most people to be close to the mean. So right here, this would be my mean. So here's my mean. And then we would take one standard deviation to the right of that would be right here. So if we add a standard deviation, we would be right here. So this is plus 1 standard deviation. If we add the standard deviation again, we'd end up here, plus 2 standard deviations. And we could keep going and find plus 3 standard deviations. So it would be right here, plus 3 standard deviations. And we could go the other way, minus 1 standard deviation, minus 2 standard deviations. And we get this breakdown of data. So when we expect everybody or every measurement to be basically the same, we're expecting to get sort of generally the same results from everybody. What happens is there's going to be some natural variability, and it ends up breaking up like this. So when we say data is normally distributed, what we mean is that A lot of the data is going to be close to the mean, 1 standard deviation away from the mean, and then fewer pieces of data are going to be more standard deviations away from the mean. So we did this in our class. If you remember, I had you come in and write down your age in months, and we put it on the board, and we were trying to determine, is this normally distributed? So in general, in one high school class, you would expect everybody's age to be somewhat around the same. So we could say it should be normally distributed. Everybody should be about the same age. So therefore, when we find the mean of the data, we should find the bulk of the data is within 1 standard deviation, even if they're higher or lower. And then, as you get farther and farther away from the mean, there should be fewer and fewer people in those categories. So when something is perfectly normally distributed, what happens is you end up getting certain percentages falling within 1 standard deviation of the mean. So if we look at, let's go back to this picture right here. If we look at this picture, here's our traditional bell-shaped curve. So say this is just a, this is a bar graph or a histogram. And you can see our values here and how many we have of each value. And we know this is a bell-shaped curve, and we can draw this bell on it here. Now, if we take that bell-shaped curve and we figure out the area underneath the curve, so if I found out the area from here over to about here, 1 standard deviation away, we would find the area in here is about 34% of the total area. And same thing on this side, we would find that 34% of the area is over here. And then if we do another standard deviation away, if we go 1 more standard deviation away, in here we would get 13.6% of the area, and over here 13.6. And then more than 2 standard deviations away, we're going to have 3.2% of the data. So you see that on here. Here's the mean right here, and if the data is normally distributed, 34% of it will be above 1 standard deviation. This is plus 1 standard deviation above the mean, and 34% of the data will be 1 standard deviation below the mean, and then etc. So this is what we are talking about when we say a normal distribution. So if something is normally distributed, this is how the data works out. All right, so what does this have to do with you? When you go to college, if you go to a competitive college like UC Berkeley, this is the way that they try and sort out students, is by using a bell curve to set their grades. So the idea here is if you are in a competitive major like engineering or pre-med is like notorious for this, they're going to try and get you to drop out of your major if you're not up there with everybody else, okay? And then the people who are really superior in their class, the teachers want to know who those people are, who's really standing out, so that they can recommend them for grad school. So this is a pretty typical way that grades are distributed in college. So if your class is graded on a curve, a lot of times people think, oh, that's great. That means I can do really bad on the test and I'll still get a good grade. Not so fast. Basically, what the teacher's going to do is they're going to say, okay, here's the average, here's the mean. I'm going to find the mean of how my students do. And usually they'll take this mean from data over several years, okay? So that if they get one really bad year where students are really slacking off, everybody can end up being over here for their grades that particular year. So usually when they say they're grading on a curve, they're using historical data to set up their grade boundaries, because professors teach the same course over and over again. They give the same final exams over and over again. So they're expecting the same results over and over again. So don't think you're going to convince your classmates to all slack off and break the curve. No. What's going to happen is there's going to be an average score for a given exam, and the professor is going to take 1 standard deviation to the right of that, plus 1 standard deviation, and 1 standard deviation to the left of that, so minus 1 standard deviation. And your professor is going to say, okay, I am going to give 68% of my students a C. Okay? So in order to get a B, you've got to be better than 1 standard deviation above the mean. And if you want to get an A, you've got to be plus 2 standard deviations above the mean. So notice how many people get an A. Only about 2% get an A. Or if we look at the real standard normal distribution numbers, that would be 2.2% would get an A. Or actually, if we look at the IQ one, 2.3%. Okay, so it depends on exactly how precise you're being on which model of the normal distribution we're looking at here. But this is pretty close to it. Okay, so the nice thing though about the bell-shaped curve, like if you are at a competitive university where they are grading on the curve, is that look, they're only going to fail actually maybe 2%. Okay, so those are the people that they're saying, you know what, this major is not for you. If you can't keep up, if you can't be up here with the 68% of the people in the class, if you're down here, the message you're going to get is maybe you're not ready for this course. Maybe you should try again some other semester, but you are not keeping up with everybody else. Okay, so this is like really important to understand, and ask your professors, how do they grade? Do they grade on a traditional like high school scale where 90 is an A, 80% and above is a B, etc., like that? Or are they using bell curve normal distribution to set their grades? Okay, I did another little thing over here where I said, let's say I had, here's my distribution of grades in my class. I wanted to give a lot of C's, and I wanted to give very few F's and a few D's and a few B's and an A. And so I ended up giving 1 F, 3 D's, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 C's, 3 B's, and 1 A. Okay, so these are my students here. These are the grades that I ended up giving. The area of these columns is going to be proportional to the probability of getting that particular grade. So, for example, if I count up all the boxes here, that's how many students there are. Okay, so the area of these columns, this has an area of 1, an area of 3, an area of 5, area of 6, 5, 3, and 1. If I add up those areas, I get an area of 24 square units. How many of those are A's? What's the area of A's? The area of A's is 1 square unit. So 1 out of 24 students is going to get an A. What percentage is that? 1, oops, let's clear all that. 1 divided by 24 gives me 4%. So here I have 4% of my students are getting an A. So this is somewhat, it's a bell-shaped curve, so it looks like it's normally distributed, but I actually was kind of generous because when there's a small number of people, it's hard to give, those exact breakdowns of only 2% getting an A because there's just not enough people in the class. So it's hard to stick to that. Okay, but what area of my curve is getting C's? 1, 2, 3, 4, 5, plus 5 is 10, plus 6 is 16. 16 square units out of 24 square units, well, that's the same thing as 16 students out of 24 students. So what percentage of my class got C's? 67%, 66 2/3, or about 67%. So the probability that you would get a C in my class is about 67%, and the probability that you would get an A is about 4%. All right, so that's a little bit about normal distribution. So we use normal distribution when we're talking about grades and grading on the curve. We also talk about normal distribution when we're talking about things like IQ, where we expect everybody to have basically a certain average intelligence, but some people are going to be smarter and some people are going to be less smart. And by the way, IQ is not fixed. You can actually work on your IQ. So if you take an IQ test and you get a certain score and you go, oh gosh, I'm so dumb, or oh gosh, I'm so smart, your IQ is not fixed. You can actually improve it. Okay, you can actually get a lower IQ. I'm not going to tell you how to do that. That's not a good idea. And also it's illegal at your age. Don't be going and trying to damage your brain. Okay? So IQ is not fixed. You can move yourself on this normal distribution. So we use normal distributions generally when we're talking about continuous data. So that leads us into today's lesson. Today's lesson is going to be taught like a college course. I am sending you pages out of a textbook. So I made a document from my favorite textbook. So my favorite textbook is right here. Let's give them credit. Cambridge University Press. So I copied some pages out of here. and put them into a PDF so I can send it to you. So you are going to read this now that I've given you a little introduction about what normal distribution is. You're going to read this, and there's a bunch of pages. Read, 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 read. This was not actually in the textbook. I copied and pasted this from the internet. Here's some directions on how to use your TI-83 or 84. So these are the directions for the TI-83. The TI-84 is actually easier because it prompts you to put in all this information. You don't have to worry about putting the commas. All right, and then they give you some examples, and they give you some formulas, and more examples, and more examples. Okay, a bunch of pages, so that is attached. And then I'm going to ask you to do some problems. These are also from the same textbook that I like so much. So you will find this also attached to our assignment. And I'm giving you some hints here. For these first problems, it's similar to the worked example 18.8. And I gave you the answer to the first one right here. And then for the second one, this is similar to, you need to use the formula from 18.6. So there's no examples of how to do these, but if you just use the formula, it's super easy. And, oh, I should give you one of the answers there. So 2i, the answer is 0.5. Okay, so the answer is 0.5 to this first one here. I think I copied that down, right? Yeah, that's 0.5. And then the last section here, these problems, these are like example 18.10, and I gave you the answer to the first one. All right, I want to give you a hint before you get started. This one right here, in order to do this one, in your calculator, it asks you, if you look at the calculator instructions, it asks you for a lower boundary, and it asks you for an upper boundary. So notice here, it's only telling us the upper boundary. So for this one, so if I'm doing, this is this problem right here, AI. If I'm doing AI, the lower boundary they don't give me. They give me the upper boundary is going to be 32. But for the lower boundary, you might be thinking 0, but we don't know what they're talking about. They could be talking about degrees Fahrenheit or degrees Celsius. We don't know what they're talking about. So we don't know what is going to be the minimum value. So if you don't know what the minimum value is, and likewise if you don't know what the maximum value is, make up a number that's like totally crazy. So lower, let's say it's degrees. I'm going to go with negative 10,000, whatever. If you could put in negative infinity, I'd say put in negative infinity, but I don't know how to do that. So just pick a really big small number. Does that make sense? On a number line, the number really far to the left, something ridiculously small. Okay, and I don't mean a decimal, okay, because a decimal or a fraction is close to 0. I mean get negative. All right, so that's my big hint for this problem right here, and if you see that anywhere else, yeah, like this one here. See, this one's actually nice. This one's actually easier because they give you the lower and the upper boundary. And so pretty much a lot of this is just playing around with the calculator. Okay, so well, I think that's it. So I'm going to post the textbook, and I'm going to post the problem set. And you've got the weekend to work this out and get them submitted. And then I will give you feedback if you're getting them right or wrong. And then on Monday, we're going to do problems in context. We're going to do word problems. Okay, so right now, this is just can you play around with your calculator and can you play around with the formulas. And on Monday, we'll actually start doing some problem solving with these and see if we can understand it. Okay, and also just for fun, I'll upload this so you can see how these breakdowns happen. But these are, it's based on standard deviations, so you keep adding a standard deviation and you get fewer and fewer data points the farther away you get from the mean. All right, and then this, be afraid, be very afraid. When your professor says that the grade is based on a curve, he's curving the grades. If they're a math teacher, it's going to be harsh, all right? Only 68% of you will get a C. So if you're okay with getting a C, no problem. But if you want an A, you are competing with the very top people in the class. And so study hard. Make sure that's you. All right. Have a nice weekend. See ya. Talk to you on Monday. I'll also be setting up another Zoom meeting so we can talk about this stuff too. All right. Bye-bye.